Low gloss and solvent-borne automotive coatings is very often misinterpreted as a chemistry or curing failure, when in reality it is frequently the optical consequence of surface texture. From an OEM RD&I perspective, gloss is not an independent material property, but an optical outcome governed by how light interacts with the cured coating surface. To understand low gloss correctly, we must stop treating it as a standalone defect and instead view it as the final symptom of upstream surface formation issues such as orange peel, poor leveling, stippling, and overspray roughness. Gloss measurement is fundamentally a measure of specular reflection. When light strikes a perfectly smooth surface, most of it reflects at a predictable angle, producing high gloss values. When the surface contains micro or macro scale texture, the reflected light is scattered in multiple directions, reducing the amount of light reaching the detector at the specified measurement angle. This scattering, not a lack of resin quality or cross-link density, is the dominant reason for gloss loss in most OEM production environments. Different texture scales affect gloss differently depending on the measurement angle. At 60 degrees, which is the most commonly used geometry for automotive coatings, both medium-scale orange peel and finer surface disturbances influence the reading. At 20 degrees, which is used for high gloss finishes, even very fine surface texture and micro roughness cause a dramatic drop in measured gloss. At 85 degrees, typically used for low gloss or matte systems, larger scale texture dominates. This is why a panel may pass gloss at one angle and fail at another, even though the chemistry is unchanged. Orange peel reduces gloss by creating long wavelength surface undulations that redirect reflected light away from the detector. Poor leveling introduces uneven film thickness and microflow lines that scatter light irregularly. Stippling creates localized droplet impact texture that breaks surface continuity. Overspray roughness introduces discrete dry particles that act as scattering points. In all cases, the resin system may be fully cured and chemically sound, yet the surface optics are compromised. One of the most common plant-level misunderstandings is attempting to correct low gloss by increasing flow additives, adjusting curing temperature, or changing resin grade without first identifying the dominant surface texture mechanism. Flow additives can improve leveling only while the film is wet and continuous. They cannot smooth a surface that is already mechanically textured due to spray mechanics or dry particle deposition. Similarly, increasing bake temperature may improve cure, but will not remove surface topography that was locked in during application and flash off. Film build plays a nuanced role in gloss appearance. Insufficient film build exaggerates surface texture because there is less material available to flow and bury substrate or application-induced irregularities. Excessive film build may temporarily improve gloss by partially masking texture, but it introduces risks such as sagging, solvent popping, and long-term durability loss. OEM specifications are designed to balance optical performance with mechanical reliability, which is why correcting gloss through film build manipulation is not considered a robust solution. Gloss approval in OEM environments is never based on gloss numbers alone. Visual assessment under controlled lighting remains critical because human vision integrates multiple optical cues, including distinctness of image, haze, and sparkle uniformity. A panel with acceptable gloss units may still be rejected if surface texture causes image distortion or inconsistent appearance across panels. Conversely, slightly lower gloss readings may be accepted if texture is uniform and visually pleasing. This reinforces the principle that gloss meters measure reflection intensity, not perceived quality. From a troubleshooting standpoint, low gloss should always trigger a surface texture diagnosis before any formulation changes are considered. Side light inspection, wave scan data, and tactile assessment provide immediate insight into whether the gloss loss originates from flow, spray, or overspray mechanisms. Once the texture source is identified, corrective actions become clear. Leveling-related gloss loss points toward viscosity, solvent balance, flash off, and temperature control. Spray mechanics-related gloss loss points toward gun setup, spray distance, overlap, airflow, and robot path optimization. Additives have a supporting role, but never a corrective role when texture is the dominant factor. flow agents, surface tension modifiers, and rheology modifiers can optimize surface formation only within a properly controlled process window. When that window is exceeded, additives become ineffective or even counterproductive. OEM RD&I teams therefore treat additives as fine-tuning tools, not defect cures. The key takeaway is that low gloss is not a root cause defect. It is an optical indicator that something upstream in surface formation has failed. Plants that chase gloss numbers without addressing texture often enter cycles of repeated adjustment with no sustainable improvement. Plants that trace gloss loss back to surface physics resolve issues faster and with far greater process stability. As this episode closes the appearance defect cluster, remember that every gloss problem tells a surface story. Read the surface correctly, and the solution becomes obvious. If you have questions about gloss failures, conflicting gloss measurements, or appearance approvals in your plant, leave them in the comments. We'll break them down in future episodes with real OEM case studies and corrective logic.